In this video, we'll talk about the other types of indeterminate forms where L'Hopital's rule can be applied. However, the main thing to realize is in order to apply the rule, you must first get into the either 0 over 0 or infinity over infinity form. The L'Hopital's rule only, as stated, works for 0 over 0 or infinity over infinity. There are a lot of other indeterminate forms, though, and so we want to figure out how we can manipulate those into the proper form to be able to apply the rule to then solve these problems. We'll start with 0 times infinity. This one's pretty easy to think about. So if I have something like 0 times infinity, how could I write that as either 0 over 0 or infinity over infinity? Thinking sort of heuristically here. Well, 1 over infinity is 0. Again, not directly, but in the form we're looking for. And 1 over 0 is infinity. So what this means, I can write 0 times infinity as either 0 over 1 over infinity, that's 0 over 0, or infinity over 1 over 0 by moving something to the bottom in the denominator. Make that be infinity over infinity. That's the idea for this setup. If f goes to 0 and g goes to infinity as I approach my certain point, then I can write the limit as x goes to c of f of x times g of x as either the limit as x goes to c f of x over 1 over g of x, or the limit x goes to c g of x over 1 over f of x, and both of those are invalid forms for L'Hopital's rule. The main thing you want to think about for these problems is you want to move the less complicated thing to the bottom, because for L'Hopital's you have to differentiate the top and bottom separately. You have to differentiate 1 over g or 1 over f, and that's not usually great. So you want to move the simpler thing down, make it easier to take the derivative later on. And now we'll see an example of that. The main example here is something like the limit x goes to 0 from the right of x times log of x. The point here is x goes to 0, and log of x goes to minus infinity. That's of the form 0 times infinity, minus sign doesn't really matter. And so we have to manipulate this to figure out how we can apply L'Hopital's rule to it. The way you want to do that here is the fact that the limit as x goes to 0 plus of x log of x is the same as the limit as x goes to 0 plus of log of x over 1 over x. So the point here is I'm moving the simpler thing to the bottom because this next step then becomes easier. This is now of the form infinity over infinity. I can apply L'Hopital's rule. And I get this being the limit as x goes to 0 from the right of 1 over x on top and a negative 1 over x squared on the bottom, which is the limit as x goes to 0 from the right of minus x, which is 0. This limit here is 0. As a warning, if you had done the wrong transition, so say you wanted to do it the other way and look at the limit as x goes to 0 plus of x over 1 over log of x. Well, what's going to happen when I try to apply L'Hopital's rule to this setup? Well, I'm going to get the limit as x goes to 0 from the right of 1, that's easy, divided by, what do I get here? I get a negative 1 over log of x squared times a 1 over x, which if I manipulate that becomes limit x goes to 0 plus negative x log of x squared, which is actually more complicated than what I started with. That's really bad. That's not the way you want to go with this because that's going to make it harder or impossible to find a limit that way. If you do it with the simpler part in the bottom, then you're in a decent spot because then your derivative becomes easier to find, it becomes a simpler expression to solve, and then you can work things out from there. Our other form is that of infinity minus infinity. Again, this could be anything at once, so we're going to have to figure out how to make this happen. In general, doing things of this form will require some fraction manipulation. The point is you're looking at something like a 1 over 0 minus 1 over 0, so what you want to think about is probably happening here. So if I can combine these two fractions, the bottom will still be 0, and there's a chance the top will also go to 0, and we can solve it out from there. That's what we have here. Limit x goes to 0 of 1 over x minus 1 over sine of x. Those both go to 0 as x goes to 0. So I will end up here with a 1 over 0 minus 1 over 0, or infinity minus infinity in determinate form. So what I want to do first is combine these two fractions. So 1 over x minus 1 over sine of x is the same thing by cross multiplying. Sine of x minus x over x sine of x. Now this, if I plug in 0, gives me 0 over 0. So I can apply L'Hopital's rule to that expression, instead of the original one, and see where that gets me. So I'm looking at limit x goes to 0, sine of x minus x over x sine of x. This is 0 over 0. I'm going to apply L'Hopital's rule, which gives me a limit as x goes to 0. The sine of x becomes a cosine of x. The x becomes a 1. And the bottom is a product rule. So x cosine of x plus sine of x. If I plug in 0 here, I get a 1 minus 1 on top, and a 0 plus 0 on the bottom. So this is again 0 over 0. I can apply the rule one more time to get limit x goes to 0. Sine of x with a negative sign, the 1 goes away. The bottom becomes a cosine of x minus an x sine of x with the product rule in that first term, plus a cosine of x. If I plug in 0, I get 0 on top, and I get a 2 on the bottom. That is not indeterminate, that is the number 0. So my answer here is 0, telling me that my original problem, limit as x goes to 0, 1 over x minus 1 over sine of x, is actually equal to 0. That's a couple other forms that exist that are indeterminate that you can solve by L'Hopital's rule as long as you do the appropriate manipulation first. You have to first get it in the form 0 over 0, infinity over infinity, and then you can apply the rule like normal to evaluate these indeterminate limits.